this talk on Swift, Apple's new programming language for iOS and in the future for the Mac desktop as well. Just to get my expectations aligned, how many of you are currently iOS developers? Okay, sort of. And Objective-C are you using right now? Yes? Okay. So I think there's two good reasons to come to this talk. One, if you are already an iOS developer, then it's obviously interesting. What has Apple done? What is this new language? How do I use it? How is it similar or different from what we have already? If you're not doing iOS yet, I think it's interesting, even from a theoretical perspective, what kind of new language somehow emerged from nowhere, really. Apple's been working on this thing in secret for at least 5 years now. Some people at Apple have started working on the Swift compiler and runtime for over 5 years ago. And so from a language design perspective even, it's interesting to look at the new language and look what Apple has finally produced. And it's also interesting because not every day a hugely popular new programming language is born. And Swift is definitely set to become one. It's going to be the language we all use for building iOS applications at some point. And already today, lots of iOS developers are very curious and trying to transition already to using Swift, at least in new application development. And so we're going to take a look at both of these perspectives. Mostly I'm going to try and assume that you aren't currently working with iOS, so just making no assumptions whatsoever, just talking about the language design in general. And then towards the middle of the talk, we'll just start building a simple iOS application. And then if you're already familiar with iOS, it's just going to be an example of how you can do the same things that you do in Objective-C with Swift. If you're not using iOS today, then it will be sort of a brief introduction, but this isn't an iOS introduction talk. We are going to focus on the language mostly. So, with that said, my name is Sasha. I work for a company called Sela. I'm actually a Microsoft C# MVP, but I've given a bunch of talks at Software Architect, and they're not all Microsoft related. This one is in particular. It's absolutely nothing to do with Microsoft whatsoever. My blog and Twitter account are there if you'd like to follow me. And the slides you can already download from my Dropbox, and I'm also going to post all the code we write today to my blog. So, let's get started. Apple has announced in June at WWDC, their annual developer conference, 3 major pieces of technology. One is iOS 8 and OS 10 Yosemite, the new versions of the mobile and desktop operating systems Apple is producing every year. Xcode 6, the new version of the development environment that Apple has been working on for years. And third, and more surprising probably, was a new programming language. Really out of nowhere. Everyone already gotten used to the horrors of Objective-C. And then suddenly a new language emerges and Apple is like, you should all use Swift. Objective-C is nice and we're not deprecating anything, but Swift, Swift, Swift. And look, all the talks at this conference use Swift. All the code samples use Swift. So all of a sudden it's as if nothing else ever existed. And that's pretty typical for Apple. If you've been following Apple for a while, they do have this tendency of making very clear and quick cuts. And they're definitely trying to push Swift very, very strongly right now. In terms of resources, if you're looking to learn more after the session, the WWDC conference actually has a bunch of nice videos covering Swift if you are a registered iOS developer. If not, Apple has released a free book. I think it's about 800 pages called The Swift Programming Language, which you can use to learn the syntax itself. And there is even a detailed grammar reference for Swift. And Apple also have a free ebook on using Swift with existing iOS applications, using Swift with Objective-C, which could also be interesting. So there are some free additional resources in addition to what we're going to talk about today. Now, why even invent a new programming language? This is a quote I really like from 2004. By Eric Gunnarsson from the C# compiler team. And he said, every feature starts out in the whole by 100 points, which means it has to have a significant net positive effect on the overall package for it to make it into the language. and he's talking about C#. And he's talking about adding small new features to C#. And they're debating very strongly whether it's worth it to add this one little new feature to the language. And then Apple comes and, well, develops a whole new programming language from scratch, which isn't like anything else, which isn't based on anything else, which isn't compatible with anything else. So why? Why would anyone invent a new programming language in 2014? And so there's lots of answers to that. And one aspect I'd like to follow with you is what's wrong with Objective-C, essentially, and why we need Swift to fix those issues. Another perspective of looking at that is trying to explain why Apple hasn't adopted an existing language, and I'll touch that briefly as well. But this is basically philosophy, so if you're willing to accept that Apple have their good reasons for inventing a new programming language, we're good to go, but I still want to spend a couple of minutes trying to explain their position. So if you look at Objective-C's popularity, Objective-C has been around for 30 years, really, 30 years, which is more than a lot of other languages, and it's only become popular because of the iPhone. Pretty much no one was actually using Objective-C before the iPhone. And so on this chart, you can see the green line over here is Swift's popularity, according to the TIOBE Programming Community Index. And the App Store was introduced in late 2008.
You mean Objective-C, yeah?
What's that?
You mean Objective-C, you said Swift. You mean that's Objective-C's?
Objective-C's,
yeah.
What did I say?
You said Swift.
Okay, yeah, so Objective-C, yeah.
Been popular in the past.
Objective-C has suddenly spiked in popularity a few months after the App Store for the original iPhone and for the iPhone 3G have been introduced. And it's evolved since. There have been lots of additions to Objective-C since 2008, but it's all been a very patchy evolution. Apple were adding features as they seemed fit at every given moment. There's lots of patches on top of patches, and the Objective-C's syntax was pretty hard already in 2008, and today it's even more complex. And so one reason to start afresh is that Objective-C has this 30-year-old history and lots of syntax which isn't really nice to use. It isn't productive, it's hard to teach to new developers, so why not just invent something brand new with no issues, with no compatibility history? That's not really what they did, but that sort of helps to understand. Now, if we look at a few little examples, in case you haven't been using Objective-C before, just to sort of shock you a little. So here's one example. Here's a method in Objective-C. And please, let's just ignore the horrible syntax. Let's ignore the fact that it doesn't look like anything else you've probably ever seen. But this is a method called index of string in array, which takes in a pointer to a string and a pointer to an array, and just tries to return the index of that string in that array. And really ignore everything else. Just focus on this particular thing. If we pass in a null string, which is totally possible, then the method returns ns not found, which indicates the string isn't in the array. It is impossible for an array in Objective-C to contain a null reference. So it just returns some placeholder value called ns not found, which sort of makes sense, I guess. But if the array is null, then the method returns 0, which is absolutely not the same as ns not found. ns not found is the maximum value of an unsigned integer, and it means the value does not exist in the array, whereas returning 0 means it does exist and it's the first element. The index 0 is a valid index in the array. And that's just something you get used to, I suppose. But it can shock you at first, right? How do you teach that? How do you explain that? Another example. So here's an obvious typo. On the left-hand side, we declare a variable of type ns mutable array, which is an array that you can add elements to. But the instantiation is actually of an ns array, which is not mutable. You cannot add elements to it. Well, this compiles. And then as soon as you try to add an object to the array, that compiles as well, but at runtime it crashes And it says, but what are you doing? You can't add an object to an array which isn't mutable. You can't add an object to an immutable array. And this is a runtime error, not a compile time error. You might get a warning in more recent versions of the compiler, but it's not a compile time error. So there's obviously a big issue with compile time safety here, with generics, right? It's not what you're used to in C#, isn't it? And final example, here we have an MS mutable array, which is actually mutable. So it's okay to add two objects to it. The first object is a string. The other is an int, the number 17. And that's fine, and that's not the issue I'm trying to focus on, although adding a string and an int to the same array sounds like trouble. But this is fine. This compiles and runs perfectly. But then you can go ahead and say, let's extract a string from the second element in that array. And that compiles, and that runs. It runs. It succeeds at runtime. You can take the int that's inside and put it in a variable of type NSString. And you can even print that string. And it prints 17. So everything seems to be working. But then you try to use it as a string. You call a method that only a string has, like string by appending string. And that crashes because it's not really a string. It's an int. So I hope by now you're kind of convinced, if you haven't used Objective-C before, that there are some issues with the language. There are some issues with what the compiler would let you do. There are some issues with type safety. There are some issues with not having proper generics in the language. And again, as an iOS developer myself for a couple of years, I sort of learned to live with that. You get used to it. You get used to occasionally investigating these nasty crashes and just figuring out what went wrong. But it's not anything you could live with in a modern language, right? You wouldn't design a language that way in 2014. And so, Apple have designed a new language, Swift, which has the following properties, at least from my perspective. It is cleaner and it looks more modern, which is pretty important. I mean, you have to sell a language, it has to look sexy, after all. It's type safe and generic, so there are generics in the language. Arrays have a type. You can't put ints in an array of strings, which sounds pretty obvious, but I mean, in Objective-C you could. The language is type safe in terms of having the compiler verify with absolute clarity the type of every given expression and every given variable. So you can't accidentally put an integer in a string variable, or a mutable array in an immutable array in a mutable array reference. So these things are not supposed to work, and they don't in Swift. The language is extensible, and we'll see a couple of examples of that. One really nasty example, actually, is custom operators. You can add your own operators to Swift. You can make up your own combinations of characters, and they become valid operators that you can use in the rest of the program. So the language is extensible in terms of us developers being able to add new features to the language. The language has at least functional roots. Some concepts will look familiar if you're used to F# or Haskell or Scala, any functional language really. One example is pattern matching, which we'll look at. Another is closures and first-class functions. So there's lots of concepts borrowed from functional languages. I find Swift to be productive, much more productive than Objective-C anyway. It's faster to write, it's easier to read. Some constructs in Objective-C, which would take 5 lines of code, are condensed to a single line of Swift. Not because there are some utility methods that do the same thing, but just because the language is more concise, if you will. Swift is still compiled to native code, which is pretty important to understand, so you don't necessarily lose performance because you're using a nicer language. And this is extremely important. Apple would never come up with a language that requires just-in-time compilation, a huge extensible runtime, a garbage collector. That's not Apple. And so Swift does not have a garbage collector. Swift has a very, very tiny, tight minimal runtime, and Swift is compiled to native code. It looks very modern, but it ends up compiled to native code, no intermediate language, no just-in-time compilation. So that's, from that perspective, it's exactly like Objective-C. And that, of course, also affects optimizations. because the application is compiled ahead of time, and there is no just-in-time compilation, the compiler can apply really extensive optimizations. The compiler can spend a lot of time improving the code quality. Even if the build takes a little longer, you get higher quality code. And that's something you don't get in Java, for example, because the actual optimizations usually occur only at runtime. And finally, this is extremely important as well, Apple recognized that there's lots and lots of Objective-C code out there, including Apple's own Objective-C libraries, and so they're not making it difficult to work with Objective-C in the future. You can mix and match in the same project, in the same compilation unit, if you will, code in Objective-C and code in Swift. So Swift code can call into Objective-C code, and Objective-C code can call into Swift code, and both directions are pretty easy to implement. So you're not throwing away any existing investments, and it also means it's pretty easy to include new Swift files in an existing iOS application, or start building a new application in Swift and bring in some libraries that you or other people have already developed in Objective-C. So these models all make sense, and it's absolutely a design goal for Apple to make this interop between Swift and Objective-C as lightweight, as fast, and as easy as possible. So these are some properties of the language, and I mean, I still have to convince you it's all true, really, because I've just been telling you about Swift. We haven't looked at anything yet. Just one final note before we start reviewing some interesting language features and then trying to build an application using this new language. Why not an existing language? Here's the question. So why couldn't Apple just sort of pay someone, pay Microsoft, pay Oracle, pay anyone just to take their existing language, license it for whatever closed source form was necessary, and use that instead of coming up with a new language of their own? And so, excuse me. I don't have a really good answer to that from a technical perspective. Obviously, Apple could have taken, say, C#, added a few features, removed a few features, and ended up with something that's more similar to C# than Swift would ever be. However, it's important to understand, at least, and again, that's a technical perspective. From a technical perspective, the things you saw on the previous slide, especially the compiled to native and seamlessly interrupts with Objective-C parts, these parts are not easily compatible with any existing language. So if you take Java or C# or C++ and add features such that they are compiled to native and such that there is no garbage collection and such that they interrupt easily with Objective-C, you end up with a different language. It's no longer C# or Java or C++. It's Apple C#, it's Apple Java, it's Apple C++. And so the whole purpose of reusing an existing language, which could be compatibility, existing libraries, existing skill sets, would sort of be lost. So you'd have Microsoft C# and Apple C#. You'd have Google Java and Apple Java. And I think, at least again, that's my philosophy, that it's better actually to come up with a brand new language which isn't trying to be compatible with anything than force the design goals I've previously covered on an existing language, really. But again, I'm not going to spend any more time on that. I've written a pretty detailed blog post if you'd like to read more. We can also discuss it afterwards. But the reality is Swift is brand new, doesn't borrow anything from C#, Java, C++, and any other language. And that's what we're going to look at from now on. So let's just get started with a few language concepts, which will also apply, of course, in the demo. So first, variables. And Swift has two types of variable declarations: actual variables, which you can modify, and constants, which you cannot modify. So for example, size and name over here are constants declared with the let keyword, whereas address is a variable declared with the var keyword. And that's something lots of languages have. Lots of functional languages specifically. For instance, Scala has var and val, with pretty much the same semantics. C++ has const, which is also pretty similar. So Swift clearly distinguishes between variables and constants. Now, interestingly, already on this slide, you can see that there's type inference for Swift variables. size and name and address do not have a type declaration, but of course the compiler can deduce the type. But you could also make the types explicit, like this city over here is of type string, and this variable pi over here is of type double. When there is an initializer, the type declaration is unnecessary. The compiler can infer the type. Strings and arrays. Swift, of course, has first-class support for strings, arrays, and additional kinds of collections. So here's a declaration of a string. Of course, you can concatenate strings with the plus operator. A cute feature, which I really started to like, is string interpolation, which Swift has as a first-class language concept. So for instance, here, when you see this slash and then brackets inside a string, it's basically an expression which is evaluated at compile time. So over here, it's the name variable, and then again a literal string, and then this expression over here, city.capitalized string, and then the string ends. So there's string interpolation, and what you put inside the brackets are arbitrary Swift expressions. And this is really nice. And how many of you are C# developers? Using C# at your day job? Okay. So C# 6, the new version of C#, the upcoming version of C#, was actually supposed to have this sort of string interpolation using a very, very similar syntax. It looks right now that it's not going to be part of C# 6, but they're still working on it. In any case, it's a really handy feature, obviously, and saves a lot of time. So you can put these expressions in brackets. Okay. Arrays. Here's an array of strings, obviously. We just put these square brackets here and then put objects inside. Arrays are strongly typed. So this is an array of strings, and you can't put integers inside, which again makes a lot of sense for anyone except ObjectiveC developers. You can also declare an array explicitly, and this is kind of weirdish syntax. String in square brackets is the array type, and then the round brackets instantiate a new object. So addresses is an empty array of strings, and then you can do this compound assignment to add objects to the end of the array. And of course, there's a bunch of additional convenience methods on arrays. So all I'm saying really is that you have nice convenient string and array types and lots of nice operators on them. One little thing that's not immediately obvious from the slide. Arrays and strings in Swift, unlike, again, pretty much every modern language, are value types. Strings and arrays are value types. So if you pass a string to another method, it's copied. If you pass an array to another method, that method receives a copy. If you return an array from a method, again, the thing that gets returned is a copy. And the Swift runtime does lots of optimizations to try and avoid any deep copies that would have to be involved. But the semantics of these types, the semantics of strings and arrays, are that they are value types. So again, you pass them by value, you return them by value. And if necessary, of course, you could pass them by reference, but the defaults are value types. So this is a really interesting design decision, I think. Again, pretty much all other modern languages assume that strings and arrays are reference types, well, except for C++ anyway. And one of the key reasons for this design decision is to enforce immutability, to make sure objects aren't accidentally modified. So if you pass an array to another method, and that method changes an array element, so it doesn't affect the original code, the caller of that method. And so Swift makes it a little harder to modify strings and arrays and other collection types because they are by default passed by value, because they are value types. Another collection, by the way, is a dictionary, and dictionaries are also value types in Swift. Again, sort of weird, but that's the way they are. Dictionaries have keys and values, and they're initialized using this very convenient syntax. They have all the obvious operators. You can subscript a dictionary and get a value or set a value. You can iterate all the pairs of keys and values in a dictionary. So there's all the obvious support you would expect from a dictionary. Internally, a dictionary is a hash table, pretty similar to C#'s, to .NET's dictionary type, except, again, it's a value type. It's passed by value, it's returned by value by default. Now, this is a famous quote. I hope you've seen it before. So just to read a couple of lines. I call it my billion-dollar mistakes. It was the invention of the null reference in 1965. I couldn't resist the temptation to put in a null reference simply because it was so simple to implement, and so on and so forth. If you think about it, all modern languages, all modern mainstream languages keep repeating this mistake, of having a null in the type system and having it by default as part of the type system. So C# strings can be null, Java strings can be null, arbitrary object references in pretty much every language can be null. Swift takes an intentionally different view with what's called optional types. By default, variables cannot be null. So for example, if you have this variable of type string, you cannot assign null to that variable. It will not compile. And even if it was an object, a reference type variable and not a value type, you cannot assign null to that reference. So by default, variables cannot be null. If you want something to be null, you have this question mark operator here. So this is a nullable int, if you'd like, or an optional int. This variable might be null, might contain a valid value. So by default, when you see a Swift type, it cannot be null. And this has pretty extensive implications on the safety of anything you write in Swift. If you see a plain variable, no question mark attached, it's never going to be null. The compiler is going to make sure it's impossible for it to be null. And that's how Apple is trying to fix that billion-dollar mistake of introducing null into the type system. And these optionals have some pretty convenient semantics, actually. So for example, I can go ahead and assign this optional with a value, which might or might not be null. And then I can ask, well, does this optional have a value? If it does, I can unwrap the optional and get the actual integer that the optional refers to. And that's the bang, the exclamation mark operator, which is pretty symmetric, right? So if you have an optional, you unwrap the optional, and you get a non-optional type. Now, you'll see a lot of these optionals and the unwrap operators in actual Swift code, because the Objective-C APIs, the iOS APIs, the current iOS APIs, all take nulls and return nulls. They are not designed with this in mind. So you'll see lots and lots of these optional types in any location where you call an existing Objective-C API. But for new Swift code, you can definitely take advantage of the fact that by default stuff cannot be null, and again, it greatly increases program safety. Another nice operator which Swift has is this optional member access syntax. So if you have a variable which is an optional, say an optional string, you can then build expressions that use question mark dot to access members of that optional. And what this means is that if customer name is not null, then we call uppercase string on customer name. If customer name is null, then the whole expression produces null and does not crash. It just produces a null value. And this, by the way, is a feature that's also going to be part of C#6. It's something the C# compiler team has also adopted. The same syntax exactly for accessing objects that can potentially be null. So that's optional types, and we're really getting somewhere. A nice feature, a really cool feature that Swift has, which is strongly borrowed from functional languages, is pattern matching. And that's essentially a switch, but it's a switch on steroids. So let's see a few examples. Suppose I have this dictionary of how many miles a particular customer has flown during maybe the past year. So I can unwrap the optional that the dictionary returns, and then switch on that. So if the customer has anywhere between 0 and 25,000 miles, then they are a premier member. If they have 25 to 50,000 miles, they're a silver member, and so on and so forth. So you see two interesting things here. One, it's really a switch on steroids. And two, there's this nice operator here, the range operator, dot dot less than, which is a non-inclusive range. So it's from 0 to 24,999, does not include the end of the range, 25,000. And This is a simple switch, really, which just uses integers and a range of numbers. But here's a little more interesting example. So we have a customer's reservation, and the reservation has a fare class for their flight. And then we can switch on the fare class. So if the fare class is F, A, J, or C, the customer is flying business or first class, and we give them a nice mileage bonus. If it's a Y or B fare class, then it's full fare economy. M or H is top tier discount economy. The default case is no bonus at all. But if the fare class has a Z prefix, and this is an expression that's actually part of the switch case syntax, if the fare class has a Z prefix, then it's an upgrade. And upgrades don't earn miles at all. So the multiplier is going to be 0. This is a pretty crazy switch statement, and it's also very, very readable. I mean, that's the kind of thing you'd want to see in your source code, not a bunch of if statements, right, or a dictionary or some sort. And so this is a part of Swift that I really like, and there's more coming up when we take a look at smart enums in Swift. So here's that's pattern matching. Functions. Swift obviously has support for functions. You can declare global functions, and you can also declare methods on classes. We'll get to that. So this is a simple function which takes an int called x and returns an int. This reminds me very strongly of the Delphi and Pascal programming languages, where there's a trailing return type, and that's the same thing in Swift. So the function is called square, takes an x, which is an integer, and returns an integer. And here's a function which returns a tuple. It returns 3 ints packed together, the powers of a particular integer. And when you call that function, you can assign the tuple to individual variables. So here we are declaring we're declaring 2 variables, square and cube. The first tuple element, which we return here, is ignored using the underscore syntax. And that's again very readable. It's strongly borrowed again from functional languages, which have very strong first-class tuple support, and Swift is no different. And again, once you get used to it, it produces much shorter, much readable code. And I mean, in many cases, you'd write a class here, or maybe return an array, and a tuple can be actually more efficient, and in some cases more readable than either option. Okay, so that's functions, and the last thing before I show you a little demo is closures. Swift has first-class support for functions. You can return a function from a function, you can pass a function to a function, you can manipulate functions the same way you can manipulate any other kind of objects. And Swift has really cute syntax around lambdas, if you will, creating a function without declaring it. So for example, I have a function here called countIf, which sort of builds on an STL algorithm from C++. It takes an array of integers and a function. The function it takes accepts an integer and returns a boolean. So the type of the pred variable is a function which takes an int and returns a boolean. And then what we do inside is just apply that predicate and count how many numbers in that array satisfy the condition. Calling that is really easy. CountIf, here's an array of ints, and here's a closure, here's a function, without declaring a whole standalone function. So n, in, and then the function body is all you really need to write. Another example is around sorting, and this is actually something I'd like to show you in the Swift command line environment. So if you install Xcode with Swift support, let me just quit this thing real quick. You get a command line REPL environment, which is actually based on LLDB, which is kind of like GDB, never mind, which you can use to evaluate Swift expressions, write Swift programs from the console. So you can use this thing, as a calculator, or you can do actual functions. So let's declare an array of numbers, like the slide does, 1, 2, 3, 4, 4, 5, 12, 1, 7, 18, and 9, not sorted. And now let's try to sort this array using a bunch of different criteria. So There is a built-in Swift function called sort, which takes a reference to the array. And notice it's a reference because arrays are value types, so we really need to explicitly indicate we're passing in a reference. And then we need to specify a function which explains how to sort this array. By the way, if we don't specify a sort function, then numbers is just going to be sorted in increasing order. But suppose we want it sorted in reverse. So I'm going to sort numbers using the function that takes an x, which is an int, and a y, which is an int. And what it does is return whether x is greater than y. And this is super verbose, but there are much shorter options available. So if we look at the output now, it is sorted in reverse. Okay. Let's sort it again so we can demonstrate the rest. I can sort this array using a much shorter syntax, xy in x greater than y. This also works. I could also do this. Do you notice the difference? We have saved one character, actually, and I think it looks a little more readable, especially if the closure is going to be multiple lines. It's a little nicer to read. So say I break it like this. A little more readable than having the closing rounded bracket at line 13. In any case, the sort still sorts. And finally, there's something for people who love Perl.
So can I just ask, if say you had a function that took a closure in the second argument and the third argument, how would you be able to use that syntax? Would it
You wouldn't. It's only for the trailing closure.
Right, it's only for the last
closure
argument. Right, okay. So it's just a syntactic gloss.
Yeah, it's odd. So the last version is simply this. Again, if you're familiar with Perl, it's all going to be very, very reasonable. So instead of just giving the parameters any names, we use the $0, $1 placeholders. The compiler knows their types are supposed to be ints because we're sorting an array of integers. So there's type inference all over the way. And we don't have to give the parameters names if we don't want. Okay? In general, this command line environment is really nice for experimenting with Swift, using it as a calculator, or even testing out some language features that you've come across. Obviously, there is an IDE for Swift, which is Xcode, and we're going to get to that very shortly. Okay. Before we move on to the more interesting features, we've got to cover classes, at least briefly. Swift, of course, has object-oriented syntax for declaring classes, inheritance, methods, properties, all the natural things you'd expect from an object-oriented language. So for example, here, the class frequent flyer has a read-only property called name, which can only be assigned in the constructor. And it has a read-write property called miles, which can be assigned anywhere. The frequent flyer class has a constructor, or more accurately, an initializer. And this is strongly borrowed from Objective-C. Objective-C doesn't have constructors. Objective-C has initializers, and Swift as well has initializers. So this initializer takes the name string and assigns it to the read-only property. We also have methods in classes, of course, and this method here takes two parameters and modifies the read-write property. Nothing particularly interesting around it. There's also support for static methods and static properties as well. And the class keyword declares a reference type, pretty much as in C#. There's also a struct keyword, which declares a value type. Again, pretty much the same as in C#. A couple of interesting features around properties. One thing that's also available in other languages is custom properties, which do not have a backing field. So here, for example, status is a computed property that only has a getter, and that getter doesn't rely on a backing field. It uses a switch expression to return whatever value is necessary. This is pretty standard. C# has it, right? This thing over here is more interesting, and that's called a property observer. You can have a property that is based on a backing field. This property here, miles, is a double initialized with 0, and you can read and write it, you can access it. It has a backing field beneath the property. But it also has a property observer in this will set block. The will set block is called just before the property is set. And it can do validation or logging or really whatever you'd like. So here, I'm asserting that we're not decreasing the customer's mileage. There's a similar feature called didSet, which is invoked after the property has been set to the new value. And you can read the old value and the new value and again apply any necessary logic. This is super useful. If you're doing C# with XAML and you're working with iNotify property change, this could be really handy. Anyway, that's properties in a nutshell. And probably one of the last features before we actually start building an app are smart enums. Swift has enums, which can be used like in C# or C++, just plain placeholders for values, other names for values if you'd like. But Swift enums can have methods. So for example, here I have an enum member level, which has 3 possible values, silver, gold, and platinum, and it has a method that says how many miles are required to attain that status. So what it does is switch on self the value of the actual variable itself. In case it's silver, we return 25,000, gold 50,000, and so on. So if you have a variable of type member level, you can ask it how many miles are required to attain that frequent flyer status. And this is nice. I mean, replaceable with other features, but definitely nice. A much nicer feature is stateful enums, enums that can contain additional state. And this again is borrowed very strongly from records in other functional languages like F# and Scala. So here is an enum called HTTP response. And it has 2 cases, error and success. The success case has a string value in it called body, and the error case has 2 values in it called description and status code of different types. You can think of this enum here as 3 distinct types. There is a base type, HTTP response, and 2 derived types, success and error. But that's just one way of looking at it if you're trying to force an object-oriented view on this problem. Another way of looking at it is that it's an enum, it's got a bunch of options, and these options have state. They can contain additional information. That's all it is, really. And the nice thing is you can switch on these enums and extract information from them. So check this out. Suppose we have a method that returns an HTTP response like that. And then I can do, okay, case it's an error, I want to take the description and the status from the error case and put them in variables so I can check the status, and if it's an internal server error, then I print out the description. Otherwise, if it's any other error where the status isn't greater or equal to 500, then we just print a general error. And finally, in the success case, I want to extract the body from the success case and print out the body. So you can have an enum that contains additional state, and depending on the state of the enum, you can retrieve the additional state as well in a single assignment as part of the switch case statement. And again, I realize it's lots and lots of syntax to process, and you probably don't remember everything now. But I'm just trying to highlight the areas where Swift is totally different from anything else you've probably seen, and definitely different from the mainstream languages we use, like C#, Java, C++, JavaScript even. Totally different, new, modern, occasionally a little harder to use and get used to as well. Okay, so just a couple of tiny features to wrap this up, the language discussion anyway. Extensions are pretty similar to C# extension methods. You can add methods and properties to any type you want, including built-in types like ints. So here is an extension for the int type, which declares a property absolute value on the int type, and a function called times on the int type. And that's totally doable, legitimate, allowed. In fact, I'm not going to cover it here, It's even possible for an extension to make a built-in type implement an interface that you made up. You can make up an interface and then decide that int implements that interface you've just created. So it is really possible to extend built-in types as well as your own types using something that's kind of based on C# extension methods but offers more functionality because, again, you can add properties and you can make types implement interfaces. And lastly, well, generics I've already mentioned actually. C# has generics, of course, first-class language support for generics. This isn't a particularly interesting example, just showing that you can build generic classes with generic methods. And again, generics are a key part of the language. The syntax here is actually very similar to any other language that has generics. But lastly, I wanted to talk about operators. Swift, unlike Objective-C, has support for operator overloading. You can define what an operator means for a type you've created or for a built-in type. And so here, for example, I have a struct that represents a complex number, and I have a plus operator that adds two complex numbers together. That's totally natural, probably makes sense. A complex type should have an addition operator. But in Swift, you can also declare your own custom operators, and that's again a pretty nasty corner of the language. So here's an operator which I intend to apply to strings. It's a prefix operator that can be applied to any string. When you apply this beautiful operator to a string, it returns the string in uppercase. And again, the operator is just this mixture of arbitrary characters over here. And then if I say this mixture of characters hello, it prints hello in uppercase. Similarly, and probably in a more useful fashion, you can declare operators like this one, which is the power operator, at least from my perspective. So this is an operator, an infix operator, and it applies to doubles. A double, B double, returns a double, and returns the power of A to the power of B. And you can use it like this, 2.0 to the power of 4.0. This is probably useful, and you can actually imagine using this as part of your math code, maybe. By the way, the reason I haven't used a single hat is that it's already taken. It's the XOR operator. So we've got custom operators in Swift, pretty dark corner of the language, but shows one of the aspects where Apple has decided to make the language more extensible, possibly to fit other problem domains. Okay, so we've taken this brief tour throughout the language, some weird design decisions, some nice design decisions, some functional languages influencing Swift, object-oriented languages influencing Swift. You see it's really a mixture of lots and lots of features. It's unlike anything else I've ever seen before. It looks a little like C#, it looks a little like Java, it looks a little like C++, it looks a little like Objective-C. It's not any of them, though. And with all that nice syntax, or nasty syntax, it's still super performant, compiles down to native, no garbage collection, no large runtime. It's pretty similar in terms of performance to Objective-C. So, apropos Objective-C, you can mix and match, as I've mentioned, Objective-C code and Swift code inside the same project. So you can take an existing application you built with Objective-C and start adding Swift files, adding new Swift files. They can call your Objective-C classes, and your Objective-C classes can call your Swift classes. The way it works is through what's called bridging headers. Your Swift code is automatically exposed to your Objective-C applications through a header that the compiler generates. If your Objective-C code includes that header, it can call Swift methods, it can call Swift functions, it can access Swift objects. In the other direction, if you want your Swift code to access your Objective-C classes, you need a different header, which again the compiler recognizes, and everything you include in that header you can use from Swift. So it does involve a little manual labor. It's not totally transparent. You can't just do anything to another language, But essentially, any type, any method you want to make available to the other language, to the counterpart language, you can make it available. And again, it's transparent. There's no marshalling, parameter translation, no super heavy-duty lifting involved. It's all really very transparent. So with that said, let's try and build a little simple iOS app with Swift. And again, if you're already familiar with iOS and Objective-C, it's just going to be an illustration that you can use the same concepts with a different language. If you haven't used iOS before, try to focus on the language and not the surrounding concepts. I'm going to take a seat for that. And go to Xcode. So this is the completed application, which we'll try to build, and it's a to-do list manager. If I run it, here's what it looks like. It's got a table view here, which shows to-do items, and to-do items have a due date, and overdue items are displayed in red, and I can add more, like check in for my flight, and I can swipe to delete items, and if I have an overdue item, I can click and snooze the to-do item for another 24 hours. And then it's only due tomorrow. So that's the kind of thing we're going to build. And well, just one more thing. If I kill the application and launch it again, it remembers the state. So it's persistent to a file. Not sure we're going to have time for all of this amazing functionality, but let's get started anyway. So I'm going to create a new project in Xcode. And this is Xcode 6, which is the only version that has support for Swift. We're creating a single view application, and you'll notice there is a language combo box. And so Swift is by default selected now. Apple's really trying to push us in that direction. And let's call this thing To-Do's Live Demo. Okay, and I'm going to put it in the same folder just to make it available to you afterwards. Okay, so we've got this project now, and you'll notice the actual code files have the Swift file extension. Unlike Objective-C, there are no header files and implementation files. That's all long gone. You have just Swift files with everything in them. Specifically, the view controller is the code behind for the main screen that we have in this application, and the app delegate is kind of like the app class in XAML applications. It's the main class that handles the whole application launch business. But the view controller, again, is the code behind for our main screen, and here's where we're going to put code. Now, I do have to spend a minute on designing the user interface itself. And this file over here, the storyboard, is where we design iOS user interfaces. And again, there have been some changes to it for Xcode 6 and iOS 8 to accommodate iPhone 6, iPhone 6 Plus, various screen sizes and orientations. I'm just going to quickly revert, disable side classes. I'm going to quickly revert to the previous behavior simply because it's easier to explain, and now it looks like an iPhone, so hopefully it's a little easier to understand what we're going to see on screen. So what do we need in this amazing GUI? We're going to need ourselves text field over here, which will take the user's input, and we're going to need a button over here, which says add. Let's just realign it, and we're going to need a table that shows the to-do items, and that's a table view. There's actually a search box somewhere over here. Never mind. UI table view, table view, table view. Table view controller. There you are, table view. Okay, I'm going to put it in here, align it like that. Awesome. And that's pretty much for the user interface itself. I do want to add a prototype cell, which is what the design for a row should look like. And I'm going to make it use right detail, because that's what the demo I've shown you is using. So here we're going to have the title, and here we're going to have the due date for that to-do item. Okay, and just gonna give it a name, this cell. Let's call it to-do cell. Great, so that's for the UI design. Now we're gonna bind this UI to our code behind. And again, it's an iOS thing. If you haven't done iOS before, it's gonna look a little weird. But essentially the way we do this is open up the view controller class side by side with our UI. Let me just delete this code over here and start dragging. So I drag this thing over to my view controller and it creates an action for me. Let's call this action add to do item. And so now whenever the button's clicked, this method is going to be called on my view controller class. And we're going to need access to the text field. So I'm creating a connection to the text field. Let's call it to do item title TF. And we're going to need the table view in a variable to do table view, I'm going to call it. And finally, I'm going to need the table view to ask the view controller, to ask the code behind class for data. So I'm going to make, again, a connection from the table view to the view controller. And I'm going to make my view controller implement an interface called UI table view data source. And hopefully that's pretty much it for the UI code behind interactions, and we can get onto the Swift side of building the app. So I'm just going to go switch back to the Swift file. Okay, so we need to provide a few methods. Table view, number of sections in table view, that's one. Table view, number of rows in section, that's 2, and table view, cell for row at index path, that's 3. Now, these method names are pretty atypical for Swift. In Swift, you'd expect shorter, nicer method names. This here is strongly influenced by Objective-C because these are Objective-C APIs. These classes, UI table view, UI table view data source, UI view controller, they are all existing iOS APIs that we now use in Swift. And so you see these incredible methods here, 2 methods called TableView, right? The first method takes a table view and a section. The second method takes a table view and an index path. And again, this is strongly influenced by Objective-C because in Objective-C, the parameter names are part of the method name. And so in Objective-C, this method down here is called table view cell for row at index path. And this method is called table view number of rows in section. And this makes Swift ugly because it has to work with the same conventions. It has to work with the same APIs that we have in Objective-C. So it definitely looks weird that you have 2 methods called table view. Means nothing. I mean, what's a table view in the method name? But again, that's the Objective-C heritage we have. In any case, the methods themselves are pretty self-explanatory. Number of sections in table view is simply the number of groups we have in our list. So that's going to be 1. Number of rows in section is just the number of items we have in the whole table. And that's, well, it's going to depend on how many to-do items we have. So I'm going to put a to-do here. And finally, cell for row at index path should return a row given an index. And again, that's going to depend on the contents of that row. With that, let's go and add a couple of classes. We're going to add a to-do class, a Swift file, call it to-do. Okay, so that thing is a to-do class. What does a to-do have? A to-do has a title, which is a string. A to-do has a due date, which is an NSDate. NSDate is actually an iOS API, well, Objective-C API, let's call it for now. A to-do class, the to-do class has a constructor, which takes a title, initializes the title, and initializes the due date to today's date. What else does a to-do class have? Probably has a property that says whether it's overdue. And that property has only a getter, so I don't have to write get here. I can just go ahead and put the computed properties body. So this is going to be something like return nsDate earlier date, nsDate earlier date due date is due date. This doesn't look very readable, but essentially earlier date returns whether the receiver is or the parameter is earlier, the one that's earlier. And so if I give it today's date and our due date, and it returns our due date, then our due date is earlier than today's date, which means that to-do item is overdue. I know it doesn't make a lot of sense, but it does. And so is overdue is all set. And one other thing we need is snooze 24 hours, right? Which is supposed to delay, to postpone that to-do item. Now, if our to-do item is overdue, then I'm just going to set the due date to due date date by adding time interval 86,400 seconds. That's 24 hours. Else, actually, if it is overdue, I'm just going to set it to 24 hours from now. Otherwise, I'm going to delay it by 24 hours. Okay, so that's the to-do class. You could argue about the business logic, but the syntax does make sense, right? Next, we're going to build a to-do collection. Okay, so this is also just a plain class, to-do collection, which contains an array of to-dos. And you'll notice I have the private variable declaration over here, and I'm using the old syntax. That's the right syntax. Now, I have a compiler error for some reason. Why do you think the compiler complains? Why this red circle? Remember, stuff cannot be null. What happens if we create an instance of this class now? What would the to-dos variable contain? Nothing. I mean, we didn't provide a value, and that's invalid. We cannot have a property which is not optional without initializing it in every constructor. So this is the compiler helping us make sure we don't end up with an uninitialized variable. So I have to add a constructor here which would initialize this thing to a new empty array, or just as well, I could just do this. And then the compiler deduces the type, and we're initializing the object to an empty array of to-dos. Okay, now we need some methods. Add, which takes a to-do and simply adds it to the array. We need a property. Let's call it count of type int, which simply returns to-dos.count. And we need a subscript operator. And again, here's an area of weird syntax. That's a subscript operator. What did I miss? Oh, the return type, which is to do, of course. So this is a subscript operator which takes an int and returns a to-do item. It could also be made read-write, but this is a read-only subscript operator. Okay, I don't suppose we need anything else, except maybe, if we have time, I'll just add placeholders for save and load to save the whole thing to a file and load the whole thing from a file. Okay, going back to the view controller, we can now implement the number of rows in section and self a row at index path methods. I'm going to add here a private var to-dos collection, simply initialized to to-do collection to a brand new object of type to-do collection. Again, notice I don't have any nullables here, any optionals, except when interacting with iOS APIs, but my stuff isn't optional. number of rows in section can then simply return ToDo's collection.count. And cell for row at index path is going to do something a little more interesting. We're going to ask the table view for the ToDo cell, which we designed in the UI designer, and that's what we return. And in the meantime, we set the text for the left-hand side label to ToDo's collection at indexPath.row.title, and we set the detail text label on the right-hand side to ToDo's collection at indexPath.row.dueDate. Now the due date is actually a date, and the text property is actually a string. So for now, I'm just going to call description on the date, but we're going to fix that later. Just going to bring this thing a little closer to the top of the screen. We've got some interesting issues here. First, you'll notice the compiler has added this optional null access operator, because the Q reusable cell with identifier returns, and this is incredible, any object optional. And that's, again, that's what you get in Objective-C routinely. In Objective-C, you have methods returning any object and optional values all the time. If you're familiar with Objective-C, any object is ID. That's what it is. In our case, though, it should be a TableView cell, because we then try to access some fields on it. So I just got to add a cast here to UI TableView cell. Now this whole thing doesn't wrap. Let's just try to make some room. Something like that. And then the cell is no longer optional, so we don't need this. And what does the compiler want over here? UI label optional does not have a member name text. So again, this thing over here, its type, oh, the docs doesn't show, but the type of this thing is an optional UI label, because again, that's the way the original API is designed. And so over here, I'm just going to use this optional dot notation to only set the property if the left-hand part of the expression is not null. Yeah.
Maybe I've missed something, but was it by casting that you've now ended up with cell not being optional?
What was that again?
Was it by casting that you've ended up with cell not being optional?
Yeah.
Right.
I cast it to a non-optional type. And so what would happen at runtime is that if it is null, it will crash.
Right, okay.
You could also cast this thing to a UI TableView cell optional and then check. But again, when you're working with a type system like Objective-C, where everything that you get could be null, there's going to be a lot of these checks. But Swift code, brand new Swift code anyway, as you've noticed, doesn't use any nulls, doesn't have to use any nulls. Okay, regardless, this thing looks pretty complete. So let's just take this for a spin. Oh, of course, we're not adding anything yet. So let's just implement add ToDo item. So over here, I'm going to create a new ToDo. And where are we going to take the text? From ToDo item title tf.text. And I'm going to say ToDo's collection add ToDo. And by the way, this thing here should be a constant. And here we are missing a parameter label. I believe we haven't seen this before, so it's a good time to mention this. I'm calling the initializer, and for no apparent reason, the compiler requires that I include the parameter name, sort of like the C# named parameters syntax. That's again Objective-C heritage. Objective-C methods require that you specify the parameter names, because the parameter names are part of the method declaration, the part of the method signature. And so Swift takes the same position with methods. Global functions you can call with no parameter names. Methods you have to call with parameter names. And actually, there are some additional complications around this. For some kinds of methods, the first parameter name is optional and the rest are required. There's a bunch of nastiness around this, unfortunately. And again, it's all because they tried to make it easy to consume Objective-C APIs. So there you have the situation where you're designing a brand new language, but you want to make it easy to use with an old, 30-year-old language. Okay, so, well, yeah, of course, adding this thing to the collection wouldn't actually make any difference to the table view. It wouldn't ever know that we've added anything. So I gotta tell the table view here to reload its data. There's actually a more efficient way of doing this, but that's good enough for now, just so we get the actual data on screen. If I run this thing on the iOS simulator, we get something pretty close to what I have shown you before, except let me just make it exactly the same. I'm gonna put it on an iPhone 5, which has the exact same size as our design surface. Okay, so now everything's perfectly aligned, and you can forget the little mishap you've just seen. Now we're going to add some to-do items by flowers. And there it is. The date description isn't real pretty, but would work for now. And we can also call dad. Okay, seems to be working, general anyway. And so I wonder what's going to be more interesting, saving this stuff to a file. Yeah, so let me just add a few lines of code to save this stuff to a file and load it from a file. And then I'll leave a few minutes for questions. The part with the swipe to delete and coloring the cells isn't particularly interesting anyway. And if you're really interested, you can review the source I'll give you. So I'm just going to head over to do collection and implement save and load. These are actually pretty easy in iOS, in Objective-C as well. In Swift, they're going to be even easier. So I'm going to add me a private property called file path, which will tell me where to store the actual data. And so here, we're going to use a method called nssearchPath for directories in domains. Again, this is an iOS API. It was around for a while. It's actually also present on the Mac desktop. And so the first parameter here is an enum, nssearchPath directory, document directory. And here's a nice feature. This part is redundant. If the compiler knows what enum it is, I can just put the enum value with no name. The domain mask is similarly user domains mask. And expand tilde doesn't really matter. Let me just align this thing. Okay, so this is the path to the documents directory that my application can use for all its files. And so what I'm going to return is path, this actually returns an array of any object. I know for a fact it returns an array of strings. Again, we're working with a totally unsafe type system and trying to coerce it to our Swift elegance. And then we return path string by appending path component to do's file. By the way, this is a great example of how the old Objective-C APIs violate the single responsibility principle on every corner, pretty much. Just think about it. The string class has a method for creating a string by adding a path component to the end of the string. Odd. In any case, in the save method, we'll just call the file path property. And then I'm going to use a class called nskeyedArchiver, which can serialize our to-dos array and write it to a file. And for that to work, our ToDo class actually has to be serializable, and we'll get to that. And on the load part, I'm just going to do...
Sorry, why doesn't the file path need an argument label?
What's that?
Why doesn't the file path in write to file, why doesn't it need an argument label?
I think I even said that. In some cases, when you call a method, you need, the first parameter needs a parameter name. In some cases, it doesn't.
Oh, right.
On constructors, specifically, the first parameter needs a label. On standard methods, it doesn't. On static methods, it does. So it depends on the kind of method. Okay, in the load method, we're going to check if the file exists. Okay, so if the file exists, we can just load the to-dos collection from that file. NSKeyed unarchiver, unarchived object with file path. Okay? Of course, an archive object with file returns probably any object optional, so we have to cast this thing to what we know should be an array of to-do items. Great. Now, the last thing we need to make this work is really just make the to-do class serializable. Because here, we're just kind of assuming that we can archive or serialize to-do items to binary data. And to make the to-do class serializable, we need to make it implement the NS coding protocol. Trouble is, and that's like an interface. The trouble is that the NS coding protocol assumes that the to-do item, that the class that implements it, isn't actually a plain class, but that it derives from an Objective-C class called NSObject. And again, this is where the type system breaks a little, but it's actually a cute example of how you can have a Swift class inherit from an Objective-C class. And that's perfectly fine. In fact, we already have an example of that. Our view controller is a Swift class that derives from an Objective-C class. And that works seamlessly, just like a C# class can derive from a Visual Basic.NET class. In any case, NS coding requires two things. One is an initializer, and the other is a method called encode with coder. This does the serialization, this does the deserialization. So for serialization, we call encode object title for key title, and encode object due date for key due date. And in the other direction, we decode object for key title and decode object for key due date. There is no reflection in Swift because there is also no reflection in Objective-C, and therefore serialization is pretty manual. And of course, decode object for key returns an any object, so we have to coerce it to a string. Oh, Xcode's gonna crash. It happens occasionally. In fact, in some cases, only the editor crashes. Yeah, okay, so it was just the editor. Don't shoot the messenger. Right, so we've got an implementation of NS coding. The only reason I've actually added that is to give you just another example of a little Swift code. And at this point, we can run this thing, add some to-do items, buy flowers, end this session, exit the app. Oh, I haven't called save. Sorry. Yeah, so whenever I add a to-do item, I'll call save, or the add method could call save, never mind. And when the GUI loads, I'll call to-dos collection.load. Okay, so on the first run, we shouldn't have anything. Buy flowers. One item is enough. close the app, run again, Live Flowers is there. Amazing. We have a useful to-do list manager, kind of. Okay, so once we've seen some Swift code, we're ready to start wrapping this thing up. Most iOS developers I know, once they see Swift, they never look back, or at least they don't want to look back. Swift does have lots of weird features that take time getting used to. If you're already coming from Objective-C, it's going to be a lot easier getting used to these features than if you're learning Swift from scratch. But still, if you've got to learn a language for developing iOS applications, Swift is going to be much easier to learn than Objective-C. There are, of course, other options, such as Xamarin, which we discussed right before lunch, which lets you write iOS applications in C#. But it's not native, at least not Apple native. Swift, on the other hand, is what Apple thinks should be the way you build iOS applications from now on. And you'll see more and more applications by Apple developed using Swift. You'll see libraries that Apple are building, which will use Swift in the future. The whole developer documentation that Apple provides has been revamped to include examples in Swift. So every single method in every single library has a Swift example as well as an Objective-C example. So Apple really are betting hard and strong on Swift. And I personally think, or would like this bet to succeed, because for me at least, Swift has been much more productive than Objective-C. Of course, you can get used to any language. You can get used to the quirks of pretty much any programming language, but Objective-C really has lots of design mistakes that Swift fixes. For the foreseeable future, though, and that's important to note, we're going to have to use both languages anyway. People really building native iOS applications are going to have to learn and know, at least to some level, both languages, because there's a huge mass of code already using Objective-C. There's so many libraries, open source libraries, using Objective-C. And if you don't know Objective-C at all, you're going to have trouble following, resolving bugs, contributing, and so on. But if you look at the iOS community over the last few months, there's lots and lots of excitement around Swift, and people are really trying to migrate as much as they can. So at this point, for example, if you look up a Swift question on Stack Overflow, you'll, in 100% of the cases, already find a question and an answer, which is really non-trivial for a language that was born, at least for us, 4 months ago, in June. So it's really gaining in traction and popularity, and I hope you see why. If you have any questions, we still have a few minutes, and of course you can come talk to me afterwards. I hope you've enjoyed the conference in general and that you've learned a little about Swift in any case. The presentation itself is over here, and it has some pointers to language features that you might find useful. I'll also put on my blog the To-Dos app that we've just built, in case you'd like to remind yourself of exactly what you've done. You're also welcome to follow me on my blog or Twitter. I'll be happy to interact with you. So we do have a few minutes for questions. Please, if you have any, go ahead. Yes?
You have to forgive me if this is a silly question. I haven't done any iOS development, not yet, but I've done various Android developments, and we have a very large code base in C++. I know that with Objective-C, it was very easy to integrate C++. How does that interact with Swift?
Right, so I'm just going to repeat the question for whoever's watching the recording. How do you interact with C++ code from Swift? Indeed, Objective-C makes it really super easy to work with C++ because essentially Objective-C is a superset of C++. Swift does not have any features for direct interop with C++. So if you have a C++ code base, you wrap it with a Swift, with an Objective-C layer, Objective-C methods or classes, and you call that from Swift. So you'll have to put in that little facade that wraps your C++ code.
Okay.
All right, well, good luck with Swift, and thank you very much for coming. Enjoy the rest of the conference.